Okay, so a quick recap of what we've covered on intermolecular forces, or IMFs, so far. So there are three main types of intermolecular forces: London forces, dipole-dipole forces, and hydrogen bonding. London forces are attractions between instantaneous dipoles. Now, instantaneous dipoles we talked about would occur on really any atom or molecule due to the motion of electrons moving around the molecule, and for brief instance being not perfectly symmetric in how it's spread out. So that creates very tiny partial charges across the surface of an atom or molecule, and those very tiny charges are what are known as instantaneous dipoles. They only last for very brief instance of time. But if two molecules are near each other, those instantaneous dipoles from one molecule to the next can create attraction. Now, you get more instantaneous dipoles and stronger instantaneous dipoles the larger the atoms and molecules are. The more electrons there are, the more surface area there is. So these are attractions between instantaneous dipoles, and the strength increases, the strength of London forces increases with increasing surface area, is the kind of simplest way to describe it that will show up on the mark scheme. Now, all atoms and molecules have electrons and therefore have some level of London forces between them and their neighbors. So nonpolar molecules, polar molecules, ones that can hydrogen bond, they all have this force. But we often don't mention it if there's one of the other forces going on, because this is considered to be the weakest of the intermolecular forces. And I've ranked them here in order from weakest to strongest of intermolecular forces. Dipole-dipole forces are attractions between permanent dipoles, specifically the opposite charges of the permanent dipoles. So permanent dipoles happen on polar molecules. So these types of forces only occur between polar molecules. So London forces happen for all molecules. They are the only type of attraction between nonpolar molecules. Dipole-dipole forces happen also between polar molecules. So if you had a nonpolar molecule, you would identify its IMF as London forces. If you had a polar molecule, you could identify its intermolecular forces as dipole-dipole forces and London forces. So it has both of those. If they wanted to know the strongest type of force, you would just say dipole-dipole forces. The third type of hydrogen bond, and by far the strongest, is something known as a hydrogen bond. Hydrogen bonds are way harder to concisely explain. It's always key to talk about how they are between molecules. So it's a strong attraction between the hydrogen in an H-nuff bond, as we've said, on one molecule, and the lone pair on a neighboring NO or F atom. So like on the neighboring molecule. It's not something you're going to be asked to define, but that's what it is. It is the strongest type of attraction. Now, by their very nature, having N to H, O to H, or F to H bonds usually makes that molecule polar. Those bonds are really, really polar. That's kind of why this separate category of IMF is created and seen. So any molecule that can hydrogen bond is also polar and therefore can have dipole-dipole forces, and all molecules can have London forces. So molecules that can hydrogen bond actually have all three of these forces going on. Okay, So these are our three types of IMFs. Here's how they rank for strength. That's an important kind of groundwork to lay. So the next thing is that you should be able to look at molecules and try to identify the types of attractions that they would have. So if we were going to compare these three molecules, like if this was a paper 2 question, and they gave you these three molecules and they said, compare their boiling points and explain the differences, something like that. So the key thing first is to look for, is it nonpolar or polar? And then to look for, does it have hydrogen bonding capability? You're going to get marks for identifying the types of IMFs and then for correctly ranking them in terms of strength. So when I look at something and I see only C and H, I know it's nonpolar. So I know that the only IMF is London forces. I see something with O directly bonded to H, and I know that it's polar and that its strongest type of attraction is hydrogen bonding. So that's the only one I'm going to name. I'm not going to mention that it does dipole-dipole and London forces, although it does also have those. And in this one, I can see that there's a carbon to chlorine bond. I know that's going to be polar, but I don't see an H-nuff bond. So the strongest IMF that this one is going to have is dipole-dipole forces. So you'd get a mark or two for correctly naming the types of IMFs in these molecules, and then ranking them for boiling point goes along with increasing IMF strength. So this is the direction of increasing boiling points. If you're going to earn the marks on the mark scheme for explaining why, you would simply have to say dipole-dipole forces are stronger than London forces, and hydrogen bonding is the strongest type of intermolecular force. It's stronger than both those other forces. And then you're done. So usually explaining a ranking in physical properties is as simple as name the types of IMFs that are relevant for each molecule, and then explain how they rank for strength. Now, this can be, there can be more complexity to it, like they can give you one like this, and then they can give you one like this, and then they could give you one like this. Right, and so the first one is the same. That would still just be a nonpolar London forces only. Now these two both have hydrogen bonding between their molecules. I can see that from the OHs. So we would still want to name drop hydrogen bonding, and that's why they're going to have much higher boiling points than the CH4, which only has London forces. Now these both have H bonding. So now we have to think of something else to distinguish them. Key difference here that I can see is that this one has more carbons and hydrogens, so it's bigger. And so the reason why it has a higher boiling point is that it's got a larger surface area, and therefore it's got stronger London forces. So again, I've name dropped all the relevant kinds of intermolecular forces, and I've explained why these things rank differently. So it could just be hydrogen bonding is stronger than dipole-dipole, is stronger than London forces, like in the first example. And it can be more nuanced. It can have two things that can both hydrogen bond, so you have to look to a different reason for why one has stronger forces of attraction than another. Okay, so that's a quick recap of what we've covered so far for intermolecular forces.